The James Webb Space Telescope found something that should not exist at the beginning of time. The early universe has a timing problem. For decades, we thought we understood the basic order of events. The Big Bang happens. The universe expands. Matter cools. The first stars ignite. Small galaxies assemble. Then, slowly, over billions of years, those galaxies merge, grow, and become the vast cosmic structures we see today. That was the story. Clean, gradual, comfortable. Then the James Webb Space Telescope looked back toward the beginning of time and found something that did not fit. Galaxies that were too bright, structures that looked too developed, black holes that may have been feeding far too early. Not 5 billion years after the Big Bang, not 2 billion, but within the first few 100 million years. At an age when the universe should still have been crawling out of darkness, Webb found objects that looked like they had already started building at full speed. And that is the problem. Not that the Big Bang is wrong, not that physics has collapsed, but something in the early universe was working faster than our models expected. Something was building galaxies in the dark before the clock said they should be ready. To understand why this matters, start with the telescope itself. The James Webb Space Telescope was not built to take pretty pictures. The pretty pictures are a side effect. Webb was built to see light that has been traveling for more than 13 billion years. Light from the first galaxies. Light stretched by the expansion of space. Light that began as ultraviolet or visible radiation, but has been pulled into infrared wavelengths by the time it reaches us. That is why Webb sees in infrared. It is not just looking farther, it is looking at older light. A galaxy seen 13 billion light-years away is not being seen as it is now. It is being seen as it was 13 billion years ago. Webb is not a camera pointed across space. It is a time machine pointed at the first pages of the universe. Before Webb, astronomers already knew the early universe was not empty. The Hubble Space Telescope had seen distant galaxies. Ground-based observatories had pushed the limits, but Webb changed the scale of the hunt. Its mirror is larger, its infrared instruments are more sensitive, and it was designed specifically to search for galaxies from what astronomers call cosmic dawn. Cosmic dawn is the era when the first stars and galaxies began to light up the universe. Before that, there was a long, dark age. No stars, no galaxies, no planets. Just expanding gas, invisible dark matter, and gravity slowly pulling structure out of almost nothing. Then, somewhere in that darkness, the first stars ignited, the first galaxies formed, and the universe became visible. The question was always, how fast did that happen? Webb's answer was uncomfortable, faster than expected. In 2024, astronomers using Webb announced one of the most important early universe discoveries yet. A galaxy called JADES-GS-Z14-0. The name is not elegant, but the object is extraordinary. Its light comes from a time when the universe was less than 300 million years old, about 290 million years after the Big Bang. That is roughly 2% of the universe's current age. If the entire history of the universe were compressed into a single year, Webb was looking back to the first week of January. And there, in that early darkness, it found a galaxy. Not just a barely visible spark, a bright galaxy. A galaxy large enough and luminous enough to be detected across almost the entire observable universe. According to the Webb team, this galaxy is around 1,600 to 1,700 light-years across, and it was forming stars rapidly. That is not large compared with the Milky Way. Our galaxy is more than 100,000 light-years wide. But for 290 million years after the Big Bang, it is shocking, because the universe had very little time to build it. This is where the word impossible gets dangerous. JADES-GS-Z14-0 is not impossible. It exists. Webb saw it. Webb's instruments measured its redshift. Its light carries the signature of extreme distance and extreme age. The real issue is not whether the galaxy is real. The issue is how the early universe produced something this bright so quickly. That is a much better mystery than science is broken. Science is not broken. Science has found a harder question. Webb confirmed the distance of JADES-GS-Z14-0 using spectroscopy. That matters. In astronomy, a pretty image is not enough. Distant galaxies can fool you. Dust, color, brightness, and perspective can make an object look older or farther away than it really is. Spectroscopy is different. It breaks the light apart and reads it like a fingerprint. For JADES-GS-Z14-0, Webb's near-infrared spectrograph detected a feature called the Lyman break. That break shifts depending on how much the universe has expanded since the light was emitted. The farther back you look, the more stretched the light becomes. For this galaxy, the redshift was about 14.3. That placed it less than 300 million years after the Big Bang. Not guessed, measured. That is why the discovery landed so hard. And JADES-GS-Z14-0 was not alone. Since Webb began science operations, astronomers have found many early galaxies that appear brighter than older models predicted. Some are candidates, some still need confirmation. Some have already been revised as better data comes in, but the pattern is real enough to matter. The early universe seems to contain more bright objects than astronomers expected to find. That does not mean every early galaxy is huge. It does not mean every headline is right. It means Webb has revealed a population of objects that demands explanation, and there are only a few ways to explain them. Either the first galaxies formed stars more efficiently than expected, or the first stars were different, or some of the light is not coming from stars at all. It may be coming from black holes. This is the twist. When Webb first began finding surprisingly bright early galaxies, some people asked whether the galaxies were too massive for the age of the universe. If all that light came from ordinary stars, and if those stars represented a huge amount of mass, then the early universe had a problem. It would have had to build massive galaxies extremely quickly. But later research showed that some early galaxies may not be as massive as they first appeared. They may be bright for another reason. A growing black hole can light up its surroundings. When gas falls toward a black hole, it does not simply vanish quietly. It forms a hot, violent disk. That disk can shine intensely. In some cases, a black hole feeding inside a young galaxy can make the entire galaxy look brighter and more mature than it really is. So the solution to one mystery creates another. Maybe the galaxies were not impossibly massive. Maybe they contained black holes that were already feeding. But then the question changes. How did the black holes get there so early? This may be one of the deepest problems Webb has exposed. In the modern universe, supermassive black holes sit at the centers of large galaxies. The Milky Way has one, Sagittarius A star, about 4 million times the mass of the Sun. Other galaxies contain black holes millions or billions of times more massive. The usual story is that black holes grow over time. They feed on gas. They merge with other black holes. They become larger as galaxies grow around them. But Webb is finding signs that black holes may have been active very early in cosmic history. In some cases, only a few 100 million years after the Big Bang. That is not much time. A black hole cannot eat infinitely fast. As matter falls in, it heats up and produces radiation. That radiation pushes outward and can limit how quickly the black hole keeps feeding. So if a black hole starts as the collapsed core of a massive star, it may struggle to become enormous quickly enough. Unless something else happened. Unless some early black holes were born big. One possible answer is direct collapse. In this idea, some black holes in the early universe did not begin as ordinary stellar remnants. Instead, enormous clouds of gas may have collapsed almost directly into black holes. No long stellar life, no supernova first. A black hole born already massive. That would give early black holes a head start. It could help explain how some of them grew so quickly. But direct collapse is difficult. It requires special conditions. The gas has to avoid fragmenting into many smaller stars. It has to collapse in just the right way. It is not something scientists can simply assume whenever a black hole appears too early. That is why Webb's early black hole candidates are so important. They may be evidence of a process we have never directly seen, a hidden shortcut in the formation of cosmic monsters. And then there are the little red dots. They sound harmless. They are not. The little red dots are compact, red objects found by Webb in the distant universe. They are small in images, often unresolved. But their colors, spectra, and brightness make them strange. Some appear in the universe's first billion years. Some may contain actively feeding black holes. Some may be compact galaxies undergoing intense star formation. Some may be buried in thick gas and dust that changes how their light appears. And some may force scientists to rethink how black holes and galaxies grew together. The important point is this: little red dots may not be one thing. They may be a mixed population. Some galaxies, some black holes, some hybrids. Some objects sitting in a phase of cosmic evolution we rarely see nearby. That is what makes them dangerous. Not because they break physics, because they sit between categories. And when nature refuses to fit our categories, science has to move. One of the most interesting recent examples is a little red dot galaxy known as CAPERS-LRD-Z9. Astronomers reported evidence for a black hole in this object from a time roughly 500 million years after the Big Bang. That black hole may be tens of millions of times the mass of the Sun. If confirmed and understood correctly, it becomes another clue that black holes were growing aggressively in the early universe. And again, the important part is not just size, it is timing. At 500 million years after the Big Bang, the universe was still extremely young. Earth did not exist. The Sun did not exist. The Milky Way was not yet the galaxy we know. And yet, somewhere in that early darkness, gas may already have been falling into a massive black hole. That is not a small detail. That is a message from the beginning. This is where the story can easily go wrong. Because the internet loves the phrase, JWST broke the Big Bang. It sounds dramatic, it gets clicks, but it is not accurate. Webb has not disproved the Big Bang. It has not shown that the universe is older than we thought. It has not destroyed modern cosmology. The Big Bang model is supported by multiple independent lines of evidence. The expansion of the universe, the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies. Webb has not erased those. What Webb has challenged is more specific. How quickly the first galaxies formed, how efficiently early gas turned into stars, how early black holes appeared, how much of the light from early galaxies came from stars, and how much came from feeding black holes. That is not a collapse of science. It is exactly how science is supposed to work. A better instrument sees deeper. The deeper view reveals a flaw in the old picture. The old picture gets corrected, and the corrections are already happening. Some of the early galaxies that looked too massive may be less massive after all. If black holes contribute a lot of the light, then astronomers may have overestimated how many stars those galaxies contained. That makes the galaxies less impossible, but not less interesting, because then the mystery shifts from galaxy mass to black hole growth. Other galaxies, like JADES-GS-Z14-0, appear to be genuinely bright because of star formation. That suggests early galaxies may have formed stars in more intense bursts than expected. The first stars may also have been different from stars today. In the early universe, there were fewer heavy elements. Astronomers call these heavier elements metals, even when they are things like oxygen or carbon. With fewer metals, gas cools differently. Stars may form with different masses. They may burn hotter. They may shine harder. A young galaxy filled with hot, massive stars can be extremely bright without needing to be as massive as it first appears. So the answer may not be one solution. It may be several. Starbursts, hotter early stars, hidden black holes, direct collapse black hole seeds, dust and gas changing how the light appears, all happening at once in a universe far more violent than the calm diagram suggested. That is what Webb has really revealed. The early universe was not a quiet nursery. It was a construction site under extreme pressure. Gravity was pulling dark matter into invisible scaffolding. Gas was falling into the deepest wells. Stars were igniting in dense clusters. Galaxies were colliding and merging while they were still young. Black holes may have been feeding inside some of them. The entire universe was smaller, denser, and more active. Things happened faster because the conditions were different. Not magical, not impossible. Different. There is another reason this feels so strange. Human intuition is bad at cosmic time. A few 100 million years sounds enormous. On Earth, that is longer than the age of dinosaurs. But in cosmic history, 300 million years is early morning. The universe had only just become transparent enough for light to travel freely a few 100,000 years after the Big Bang. Then came the Dark Ages, then the first stars, then the first galaxies. By 290 million years, Webb is seeing galaxies at the edge of what we thought would be possible to detect. And it is not seeing only darkness, it is seeing structure, it is seeing light, it is seeing the first architecture of the cosmos already underway. That is why JADES-GS-Z14-0 matters. Not because it is the biggest galaxy, not because it is the most beautiful, but because it is a timestamp, a marker, proof that galaxy formation was already advanced enough to make something visible, bright, and chemically interesting less than 300 million years after the Big Bang. There is also an important chemical clue. Webb observations of JADES-GS-Z14-0 suggest the presence of oxygen. That may sound ordinary. It is not. Oxygen is not born in the Big Bang in large amounts. It is made inside stars. Then those stars have to die or shed material to spread oxygen into their surroundings. So if oxygen is present in a galaxy less than 300 million years after the Big Bang, something had already happened before we saw it. A generation of stars had already lived. Some had already died. Their material had already mixed into the galaxy. That pushes the timeline even harder. The galaxy Webb sees is not the first moment of activity. It is evidence of earlier activity we have not directly observed yet. In other words, by the time we see this galaxy, the universe had already been working. This is the part that should make people stop. Webb is not only seeing early galaxies, it is seeing the results of processes that began even earlier. The first stars may be hiding beyond the current limits of detection. The first black hole seeds may be hiding there too. The first chemical enrichment, the first violent collapses, the first moments when simple hydrogen and helium began turning into the ingredients of planets, oceans, and eventually life. Webb is not at the beginning yet, it is near the beginning, and already things are complicated. So what exactly did JWST find that should not exist? The honest answer is this: it found objects that should not exist if our older expectations were too simple. It found galaxies that formed earlier and shone brighter than predicted. It found clues that black holes may have grown quickly or started large. It found compact red objects that do not fit neatly into the categories we had ready. It found oxygen in a galaxy seen less than 300 million years after the Big Bang. And it found that the early universe was already capable of complexity. That is the discovery. Not a broken universe, a faster one, a stranger one, a universe that began assembling its first structures with terrifying efficiency. The next few years will be critical. Webb will keep looking deeper. It will measure more spectra. It will separate true early galaxies from objects that only look ancient. It will identify which little red dots contain black holes and which are compact star-forming galaxies. Future observatories will join the work. The Roman Space Telescope will survey huge areas of the sky. The extremely large telescope in Chile will study distant objects with enormous ground-based power. Together, these instruments may map the missing chapter between the Dark Ages and the first mature galaxies. And somewhere in that chapter is the answer. How did the universe switch on? Not poetically, physically. What collapsed first? What ignited first? What fed the first black holes? What made the first galaxies bright enough to survive 13 billion years of travel and arrive in Webb's mirror? The early universe has not been lying to us. It has simply been too far away to interrogate properly. Hubble gave us hints, Webb gave us evidence, and the evidence says the beginning of time was not slow. It was not empty. It was not simple. Within a few 100 million years, the universe was already forming galaxies, forging oxygen, feeding black holes, and lighting up the dark. That should make us cautious, because every time we build a better telescope, the universe becomes less comfortable. Not less understandable, less comfortable. The clean story becomes messier, the timeline becomes sharper, the exceptions become the clues, and the things that looked impossible become the places where the next theory begins. JADES-GS-Z14-0 is not the final answer. The little red dots are not the final answer. The early black hole candidates are not the final answer. They are the first pieces of a new map. A map of the universe before it looked like the universe we know. Before spiral galaxies filled the sky. Before planets circled heavy element-rich stars. Before carbon chemistry had time to become biology. Before Earth, before the sun, before anything existed that could ask where it came from. And yet, in that darkness, the machinery had already started. Gravity was already building, stars were already dying, black holes may already have been feeding. The universe was already becoming itself. That is why Webb's discovery matters, not because it destroys what we know, but because it shows that what we know is incomplete in the most interesting possible place. The beginning. The place where everything started. The place where the first light became the first galaxies. The place where the universe began turning simplicity into structure. The deeper Webb looks, the more that beginning refuses to be simple. And that may be the real revelation. The universe did not wait patiently to become magnificent. It began building almost as soon as the laws of physics allowed it. And now, for the first time, we are close enough to watch. Thanks for watching, and if you want to follow the evidence to the edge of time, subscribe to Cosmorium 4K. The next mystery is already waiting in the dark.